So guys, a couple of applications now of rates of reactions, and more specifically catalysts. The first one we'll look at is a catalytic converter. Effectively, a catalytic converter is placed into the exhaust system of a car. Here you see it marked in just after the engine. In the engine there is pistons. The pistons are where the fuel is burnt effectively, and the fuel is burnt there in a lack of oxygen. So you get the production of a gas, carbon monoxide, and sometimes that happens in homes as well if there isn't sufficient ventilation. So when there isn't sufficient oxygen present, what can happen is carbon monoxide is formed in the combustion of a hydrocarbon. That's something that contains hydrogen and carbon instead of carbon dioxide. So that's one of the gases. Also in the car engine, nitrogen monoxide or nitric oxide is produced, and it is the compound NO. NOx is another name for it, or so at least one of the NOx family. And that gas is highly toxic, and we want to try and prevent that from entering the atmosphere as much as possible. So sometimes you hear about this they measure the levels of NOx or nitrogen oxides in the air along as an indication of pollution from combustion engines. Normally nitrogen would never form a compound when it's in its form of N2, because it's obviously that's where we use it in bags of crisps and that. It's a very, very stable molecule, but because of the high temperatures produced by the spark plug in the piston of the car engine, the normally very stable and unbroken triple bond between two nitrogen atoms that makes up 79% of our atmosphere is broken. So the N2 is broken and you form NO. And also in the engine you can have some of the fuel, some of the hydrocarbon, the petrol, unburnt or at least not burnt completely. And that means then that the unburnt hydrocarbons, whatever's left of them, will also leave via the exhaust system, and they'll enter the catalytic converter. And the role of the catalytic converter is essentially to convert those harmful gases to less harmful gases, and indeed this is what it tries to achieve. The actual makeup of it, the reason it's called a catalytic converter is inside the catalytic converter we have the presence of a catalyst. Now it's a transition metal, either platinum or palladium or rubidium, so it's some one of those metals normally. Transition metals, that's one of the characteristics of transition metals. They're very, very good catalysts, and they will convert the gases I mentioned already, NO, CO and HC, so some hydrocarbons, and convert those to nitrogen gas, which is back to that stable one that makes up 79% of our atmosphere, or 78% of our atmosphere, carbon dioxide, which we ourselves produce and plants take in. It's essential to plant life. And then from unburnt hydrocarbons you'll also have some water formed. So sometimes out the back of a car, if you're stuck in traffic and you can see water coming out the exhaust, that is a normal occurrence, and it's due to the catalytic converter working well. Sometimes a catalytic converter, they're not perfect by any means. They need time to heat up. They won't work in the first minute or two, or if not longer. So they're not perfect by any means, but they're definitely put into the exhaust system to prevent these harmful gases from entering the atmosphere. The other thing then is these catalytic converters can get poisoned. That effectively means that the catalyst in them is somehow inhibited. And in this case what happens is the catalyst is normally blocked off from these gases. And things that can block off the catalyst, the platinum, palladium or rubidium, whichever one of those metals is used, is something like lead. So lead it used to be in petrol to improve the octane number of the fuels. That's how well they burnt. But in fact what happened was the lead now in a modern engine would do great damage because it would block the catalyst. So lead is an example of catalytic converter, poison if you like. And another one would be silicone. Sometimes if oil is put into a car engine, silicone can get into the exhaust system, and that too blocks the catalyst. That's what a catalytic converter looks like. It has a metal structure on the outside, and then in there it has ceramic beads, and on those ceramic beads you have the presence of the catalyst. And you see it as another application, not alone as an example of heterogeneous catalysts, because the gases are obviously in the gas phase. The catalyst is a metal, it's in the solid phase, so they're in two different phases, so it's heterogeneous catalyst. But in addition to that, it's a nice application of increasing surface area. That's why, if you like, when you cut through the catalytic converter, you'll see something like this, which is a honeycomb structure. It maximizes surface area, so that when the gases are being pumped through it, they most likely will come in contact with the catalyst. And that's essentially it. Now you would need to know this balanced equation here, at least you should know it. Carbon monoxide, there's a nitrogen monoxide, and there's the three catalysts. Obviously catalysts are written above the arrow, they're neither reactants nor products, and hopefully we're quite clear on that now. They simply alter the rate of the reaction, and in this case they alter the rate of the reaction of causing carbon monoxide and nitrogen monoxide to form carbon dioxide and nitrogen. And then the presence of obviously the coefficient of 2 here and 2 here and 2 here is to balance the equation. But they're the two gases coming out of the car engine, if you like, out of the pistons of the car engine, and then hopefully that's the only thing coming out of the exhaust, carbon dioxide and nitrogen. Now carbon dioxide is a greenhouse gas. It's not that it's not harmful, but it's definitely less harmful than the combination of the two of these, and that's why catalytic converters are placed into the car engine. I've mentioned this already, or into the exhaust system of the car engine, I should say there. I've mentioned this already, that catalytic poisons, they effectively inhibit the catalyst, and probably the most straightforward ones are lead, because that used to be traditionally present in petrol, and then maybe perhaps silicon.